Colleagues, good afternoon. I welcome you all. I would like to present you my talk, Machine Learning to Support City Development Challenges. My name is Danila Parygin. I'm head of R&D projects at UC Lab. The city management related tasks are our core business, and let me just explain how we approach this problem area. We work a lot with mapping data, different GISs, and GIS data is an integral part of any solution related to the life of a city. So what can people see in general maps, like Google, for instance? Yes, we have a map with some depiction of objects, and we have a real aerial picture, a fresher one, which hasn't yet been updated in the general use system. For general use, it may not be a problem because global services update this information quite often. This being said, you may encounter a situation where the information that is required that is more up-to-date, and this problem may rise when you move from just curiosity to real situation analysis. I've just demonstrated how can look in real slide, what can be present and what can be missing in pictures. For instance, not all of the buildings are shown, not all of the roads are shown. Also, for instance, not all the trees and green areas are shown. So having analyzed the situation and going through different maps and different services, network services, we identified a number of objects that it would indeed be interesting to learn more information about. In particular, this is a small list. It's parking areas and cars on them, quite a relevant topic for all cities, considering the growing automobilization process. It's greenery, the topic quite relevant to cities in Europe and the US, and is gaining traction in Russia as well. So knowing where different plants are, park areas in cities, and what's their condition. Then, as already mentioned, infrastructure items, roads, water items, railroad infrastructure that can actually take up quite a lot of space in cities, sometimes right in the downtown, right in the central area. Also, cities are growing, and questions are being raised regarding building new buildings put in already densely built areas. And also a question, how are cities and towns structured, talking about private houses and high-rises. So we've tried to identify these questions in our research. Firstly, we wanted to focus on plants, woody plants. So we present our first solutions in this area. At that phase, we were using a tile classification, but then gradually moved to the segmentation of objects in images. In particular, these two examples are about the identified greenery in St. Petersburg and Moscow. And the system demonstrated that it was quite useful. They said we were using just a regular space imagery that Google and Yandex are making public for the territory of Russia. I must say that for American, European cities, these services have more detailed images. But nevertheless, this makes the whole problem even more exciting for Russia. So, of course, space imagery is also available on a paid basis, and If you take Intelsat images, their quality is not good enough to get details. So in this case, using public images, we decided to assess the availability of parking spaces. Like, for instance, we tried to identify vehicles on such images and to find the parking spaces. Basically, there was a customer, our customer in Vladivostok, asked us to help them assess the parking capacity in the city near particular shopping malls. So we used a combination not only of machine learning, we were identifying the vehicles, but we were also differentiating. So you can see the distribution of red dots on the map. It's where we put the vehicles recognized on the map, and after that we detracted the cars on the road. This way, combining GIS tools with cartography and machine learning, we were able to use publicly available images to count the number of vehicles on parking spaces. And based on that, we proceeded to develop our general service that would include all the types of objects that I've mentioned. In order to implement that, of course, you need initial data. There's no way to get past this stage. We manually, using our own vision, identified and highlighted several types of objects. Quite a lot of them were prepared, and different types of building, multi-floor, high-rises, cottages, garages, industrial structures, whatever I listed. So for each image, a certain mask was built that was then used for training. In terms of architecture, we used the popular UNet architecture. It was partly used out of the box, but there were some modifications implemented, consideration being given to the different types of objects that we were going to identify, that we need to find. But the end result required additional development. In this connection, we used a number of auxiliary algorithms. Like, for instance, in addition to recognition of contours in the image, we used the simplification algorithm that allowed us to smooth out the images of recognized objects, such as buildings, for instance. It's quite obvious that buildings are composed, building images are composed of direct lines, whereas they were not shown this way, so we corrected these things. Another task was to build a single map. So basically, once we've identified the images of some object, then in itself it may have less value, but it needs to be linked to coordinates, and that goes for sure. And also, it shouldn't be used standalone. It should be used as part of the overall system. For that, we created a tile system where we would recognize the images by the elements, 256 by 256 pixel, and then we would merge them and get the overall map, and that could apply both to a fragment of a territory and also to quite a large territory, just like the big services do. The architecture of the solution that we developed has been, well, was built. It had two server parts. This is because the principle of the implementation of the end-user service that we identified presupposed its web implementation for user access, but we ran our calculations on the cluster. So all the user requests are being processed on the cluster. So this is why we offered this architecture. And at the end of the day, the following technology stack was used. It's a Python, libraries for it, again, tools to train models. The training was done in the cluster because our lab resides at Volgograd Technical University. We also have a cluster, and it was used as a basis to train people to work on the accelerators that they use. The end solution that we offered is a simple and convenient service that in several clicks allowed you to get the final information about the territory. So basically the user can go to a server, choose a territory that is very of interest to them for assessment, and well, here is the list of the authorities or communities that they need to get in touch with. So you can see the end-user service the way it is. Just like in the usual approach, we use a mouse to identify the area, then choose the objects in the drop-down list to the right, and finally we recognize, well, the purple color here denotes buildings, and the green color denotes trees. So on the whole, this result served as a starting point, but unfortunately it also needs some explicitly problematic application. It's about unlawful construction, and also we can use just one request to cover quite a large territory, and you won't be able and this will include control of the territory and, for instance, parks that the city administration has to take care of. It can also be used in terms of monitoring the industrial or construction sites. Of course, satellites can be used for that. But this technology is also quite applicable. So we got quite a universal service that could, in principle, get development. And we ran the testing in large cities where accuracy of recognition is very important. And also considering that cities are quite large and the living system, the accuracy of detection is also very large. Thank you. That brings me to the end of my presentation. I'm happy to take questions.